Hello students, welcome back to today's class on square roots and cube roots. In the previous classes we learned about exponents and powers, and extension to that we are going to focus only on squares, square roots, cubes and cube roots. Right? My name is Avinash and I am a graduate from IIT Kharagpur. Let's continue today's session. So what is exponents and powers, which we have already discussed in the previous classes? Powers are used to represent exactly how many times a number should be used in a multiplication process. How many times the same number should be multiplied to itself, right? For example, I have 5 into 5 into 5. How many times? We are multiplying the same number 3 times. Okay, so 3 into 3 into 3, 1, 2, 3, 4, 5, 5 times we write as 3 top of that 5, 3 power 5. We read that as 3 power 5 or 3 raised to 5. 3 raised to 5, or simply we say 3 power 5. Okay. 10 into 10 into 10. So we use 10 3 times. We multiplying 10 3 times, so 10 cube. How we read this? 10 cube. Okay. So 10 power 3, we read it as 10 cube. 10 into 10, we write that as 10 power 2, which we read as 10 square. So today our goal is to learn about squares and cubes. Squares and cubes. Okay. So moving ahead, let's try to understand what is a 10 power 9. We already discussed that in the previous classes. 10 power 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is how you can simply write 10 power 9. 10 power cube, 3 zeros, 10 power 5, 5 zeros, 10 power 7, 7 zeros, 10 power 9, 9 zeros. 6 cube, 6 into 6 into 6. 6 into 6 is 36. 36 into 6, 6 6 are 36. 6 3 are 18, 19, 20, 21. So that becomes a 216. That becomes a 216. Okay. So 4 cube, 4 into 4 into 4 into 4. 4 4s are 16 into, again 4 4 is 16. So 16 16s, maybe 256. Let me check that. 6 6 are 36, 6 1 6 7 8 9 6 1. That becomes 256. Okay. So 256. So this is how you find the values, right? Now, let's try to understand about square roots and cube roots. Before that, let's try to understand about squares and cubes. Then we'll go forward for square roots and cube roots. In today's class, we're going to discuss about squares and cubes. Okay. Express the following numbers as a product of equal factors. Product of equal factors. That means if let's say you have a number 6, and you need to express that as a factors, a product of factors. We can write that as 2 into 3 or 1 into 6, right? 1 into 6, 6 into 1, 2 into 3, 3 into 1. So all these are expressing the same number in terms of its factors, product of factors. Now in the same way, let's try to understand how to write 1. 1 we can write as 1 into 1, the same number being multiplied twice. 2 we can write it as 2. I don't think we can write in any way. Okay, let's try to ignore that. 4 we can write as 2 into 2. 9 we can write as 3 into 3. 16 4 into 4, and 25 5 into 5. Okay, this is how we write all this. 1 into 1 we write as 1 raised to the power 2, or simply we read that as 1 square. We read that as 1 square. 2 into 2, it is a 2 square. 3 into 3, 3 square. 4 into 4, 4 square, and 5 into 5, 5 square, and still continuing, we get 6 square, 7 square, 8 square, whatever the numbers are, right? Okay, so this is how you write a square. For example, I write 10 square, which means that 10 into 10, so which is 100, correct? I have 121, we can write as 11 into 11, which is a 121, which is 11 square. 12 into 12, 144, 13 into 13, 169, okay? The next one you get 144, the next 169, 14 into 14, 15 into 15 is 225, 16 to 16, 256, just now we solved that. So in that way, we have a number, the same number being multiplied. Again, we get that as a square. We read that as a square, okay? The next one we're going to learn about, you might have observed in the given pattern, the numbers are expressed as a product of 2 equal factors. Product of 2 equal factors, just now, right? 100 we express that as 10 into 10. 81, 9 into 9. 64, 8 into 8, right? So those type of numbers, such numbers are called perfect squares. Those numbers are called perfect squares. So now tell me, is 81 a perfect square? Is 81 a perfect square? Yes. Why? 81 can be written as 9 into 9. 81 can be written as 9 into 9, right? In the same way, I will go for 64. 64, is it 6 into 6? No, 8 into 8, okay? Let me write that properly. 64 is 8 into 8. What about 70? Is that a perfect square? 70, no. 70 is not a perfect square because we don't have 7 into 7 or 8 into 8, 9 into 9, never we get 70. That is not a perfect square, okay? So in the same way, let's try to understand more about that. So 9, 3 into 3, yes, that is a perfect square. 49, 7 into 7, 1.44. Carefully, very careful. 1.44 is a 1.2 into 1.2. Is there any difference between the first, second, and third, fourth? 1, 2, and 3, 4. Yes, we have a difference. What is that? We have perfect integers here, perfect numbers, right? But here we have decimals. All the same thing. 1.44 is 1.2 into 1.2. This is exactly the same what we are discussing for perfect squares. 2.25 can be written as 1.5 into 1.5, right? 6.25 can be written as 2.5 into 2.5 into 2.5. That is 6.25. 2 by 3 into 2 by 3, we'll get it as 4 by 9. 4 by 9, which we can write as 2 by 3 whole square. 2 times we are multiplying, so in whole square. So all these we are going to discuss a few things about this one, about the difference between the first, second, and the difference between the third and fourth. There is a small difference. What is that? The first two are perfect integers, but not the next two. Okay. So what difference that makes according to that? In the case 1 and 2, we have noticed, right? What we have noticed? The perfect square numbers 9 and 49 are integers. 9 and 49 are integers. Yes, 3 into 3 is 9. 3 into 3 is 9. It's a perfect integer. 7 into 7 is 49. It is a perfect integer, right? So they are perfect squares and integers. The general form of such perfect square number is m equal to n into n. Okay, same 49 can be written as 7 into 7. Such type of number is a perfect square. Okay, so 100 we can write as 10 into 10. 121 we can write as 11 into 11. So all these are the same perfect numbers, perfect squares. Okay, in the case 3 and 4, where we discussed with decimal values, the perfect square numbers are not integers, hence they are not square numbers. So again, when we are discussing about squares, we are only discuss about integers. Okay, so the general form of such perfect square numbers, but these are not square numbers. What we have discussed, 1.2 into 1.2 is 1.44, right? We have discussed a couple of examples based on that. Those examples, those numbers which we are dealing with, fractions or decimals, will not come under square numbers. Okay, we need perfect integers for that. Okay, moving ahead. If an integer m is expressed as n square, where n is an integer, then m is a square number or m is a square of m. Okay, so if m can be expressed as n square, for example, 144 can be expressed as 12 square, which is actually 12 into 12. Right, 169, 13 into 13. In that way, if we can express that m as n square, where n is again an integer. Okay, we need to understand that, where n is an integer. That's the reason. In the before examples, we have 1.2 into 1.2. We are not considering that as a square numbers. Okay, so we need an integers. Yes, we have such type of numbers, and then we say m is a square of m. 144 is a square of 144 is a square of 12. 169 is a square of 13. 225 is a square of 15. A perfect integer should be there in place of n. Correct? Next. A perfect square. So we are going to learn two things, perfect square and square number. What are these two? A rational number that is equal to the square of another rational number. What is a perfect square? A rational number that is equal to the square of another rational number. Okay. For example, we have the same example. We'll take 225, which is a square of the other number, right? So we can say that as a perfect square. Next. But what is a square number? What do you mean by square number? There is a difference between these two. Square number, an integer that is a square of another integer. An integer that is a square of integer. The perfect square, you can have even decimals also, but not in the case of a square number. Square number is perfectly with integers only. Okay. Next. All square numbers are perfect numbers. Yes, that's correct. Okay. All the square numbers means integers. Square numbers means all integers. Okay. So all square numbers are perfect square, but all perfect squares are not square numbers. But all perfect squares, for example, 1.2 into 1.2, it is 1.44. We are not getting in integers here, right? These are not integers, but all perfect squares may not be square numbers, okay? Next one, what else we are going to learn here? 2.25 is a perfect square number. It's a perfect square number because it can be expressed as 1.5 into 1.5. It is not a square of an integer. It is not square of an integer. Okay. Therefore, it is not a square number. Understand, there is a difference between. It is a perfect square. We are getting 1.5 into 1.5 is 2.25, but they are not integers. So, as they are not integers, we should not keep them as a square number. Whenever you read that square number, you should try to understand that it is only reserved for integers. That word square number, that term square number is only to be used when you have integers. It's only to be used when there is a integers. Okay. So, in the same way, 2.25, we can go with any other example. For example, 2.2 into 2, right? Or 2.1, 2.1. Maybe, I'm not exactly sure. Maybe 4.41. Once again, please check that. 4.41 is a perfect square number, but it is not a square number. It is not a square number. Understand, there is a difference between these two. For a square number, you should always have an integer with you. Okay. What else? Properties of a square numbers. Let's try to understand a few properties about that. Observe the digits in the unit place of the square numbers. Okay. Observe the digits in the units place of a square number. For example, if you go for 1 into 1, we get the units digit as 1. 2 into 2 is 4. 3 into 3 is 9. 4 into 4 is 16, where the units digit is 6. 5 into 5 is 25, the units digit is 5. 6 into 6 is 36, 6. 7 into 7 is 49, 9. 8 into 8 is 64, we are having 4 again. 9 into 9 is 81, 1 again. So 10 into 10, we get 0 at the end, that is 100. So once carefully observe what all units digits we are having here. We have a 0, yes, 10 into 10, 20 into 20, 30 into 30 will get 0. We get 1 we get either 1 into 1 or 9 into 9. So we get 1 as units digit of a square. Do we get 2 anywhere? No. Do we get 3? No. Do we get 4? Yes, 2 into 2 is 4. So we get 4 here as well as 4 here. Again 25, right? 5 into 5, so we get 5 again. 36, do we get, this is 6. 6 we get 6 into 4 into 4 as well as 6 into 6. So we also get 6 as the ending digit of a square. Do we get 7? No. Do we get 8? No. Do we get 9? Yes. 9 again we'll get at 3 into 3 and 7 into 7. So these are the number, these are the units place where a square number can end with. Okay, we cannot have 2, 3, 4, 5, 6, 7, 8. These 4 digits cannot come as a units digit of a square number. These digits cannot come as a square of a number, right? Square of a number. Whatever number you take, let's say 101 into 101, 101, 102 into 102. 1542 into 1542. You may get some units digits from here, but not from here. You yourself can calculate that. Take any random number, 22 into 22, 23 into 23, 24 into 24, 25 square, 26 square. Whatever number you take, your units digit will always end with these numbers 0, 1, 4, 5, 6, 9. Wherever you have 2, 3, 7, 8, you can straightforward say that there is no perfect square for that. There is no square of that. Okay. Next. Properties of square numbers once again. Do you observe all these numbers ends with 0, 1, 4, 5, 6 or 9, 2, 3, 7, 8. These numbers will not come. Okay. At units, none of these end with 2, 3, 7, 8. So what we can say with that? The numbers that have 2, 3, 7 or 8, the numbers that have 2, 3, 7 or 8 in the units place are not perfect squares. The numbers that have 2, 3, 7 or 8 in the units place are not perfect squares, Right? Next one. Can we say that all numbers ends with 0, 1, 4, 5, 6 or 9 at unit place are square numbers? Can we say that? For example, I'll give you 25. 25, you know it is a 5 into 5. So yes, it is a perfect square. But what about 35? 35, we cannot express that as square of a number. Not 5 into 5, not 6 into 6, not 7 into 7, whatever number you cannot do that. At most, you can express that to 5 into 7. But these two are not the same numbers. So no, we cannot. So what is the answer? Not all the numbers ending with 0, 1, 4, 5, 6, 9 are perfect numbers, are perfect square numbers. Not all, only few. But if it is a square number, definitely it should end with these 6 digits. 0, 1, 4, 5, 6, 9. No other number. I'll give you a big number. Okay. 1, 4, 2, 3, 5, 6, 9, 4, 1, 0, 2. Now my question is this number a perfect square? Is a square number? Answer is no. Why? Why? Because the last unit digit is ending with 2, which cannot happen. The unit digit of any square number cannot end with 2. It should end with 0, 1, 4, 5, 6 or 9. It should end with a 0, 1, 4, 5, 6 or 9. Right. The next one. Write the squares of 1, 9, 11, 19, 21. Okay. So 1 square, 1 into 1 is 1. 9 square, 9 into 9 is 81. 11 square, 11 into 11 is 121. 19 square, what is 19 into 19? 9 9s are 81, 9 1s 9. 9 plus 8 is 17. Again it is 19, so it is 1, 16, 361. That becomes a 361. 19 into 19 becomes 361. 21 square, which is 21 and 21, which is a 441. So carefully observe what's happening here. Units digits of every number 1, 9, 11, 19, 21, all these numbers are ending with 1. Okay. So 1, 11, 21, 31, 41, 51. So all these squares will definitely end with number 1 as well as 9, 19, 29, 39, 49. So all these number squares will also end up with units digit as 1. Okay, that whenever you see a perfect square ending with 1, you can directly see either the number will have 1 or 9 in the units place. Right? It's a very straightforward, no need to learn anything. It's a basic mathematics you can understand with examples. Correct? A very beautiful approach. The next one, if a number has 4 or 6 in the units place, then the units digit in the square is always 6. Okay. So 14 into 14, I don't know, whatever it is, the unit digit is 6. So it is 196. Okay. 16 into 16, it is a 256. 4 into 4, it is 16. 6 into 6, it is 36. So you can see all the units digits are the same. So whenever you have 4 or 6 as the number, the square of that number will always be 6. Right? You can take any other example, no problem for that. Let's go for one more. So which of the following have 1 in its units place? Which of the following has a 1 in its units place? So there is some printing mistake. It's not exactly 1. It should be square. 126 square, 192 square. Which of the following have 1 in its units place? Okay. So there is some mistake here. Maybe 126 square, 179 square, 281 square, and 3632 square. Okay. Even the same thing that goes ahead. 116 square, 228 square, 324 square, and 363 square. Okay. So based on the units digit, you can directly say that which number. Okay. Based on the units digit, we can say that which number will be in its units place. Right. The next one, that I will come back to that in the next class once again. So yes, so we have some patterns that we need to fill. A very beautiful approach, you can see. 1 is 1 plus 1. 1 is just 1. 1 plus 3 will give you 4, which is 2 square. 1 plus 3 plus 5, careful observe, we are just adding odd numbers. We're just adding odd numbers of 1 plus 3 plus 5, 3 square. 1 plus 3 plus 5 plus 7, we're adding 4 numbers, so 4 square. The first 5 odd numbers, 5 square. The next 6 odd numbers will give you 6 square, which is 36. Next 7 numbers, 1, 2, 3, 4, 5, 6, 7. 7 becomes 49, which is this one is 6 square, and this one is a 7 square. That is how you can try to write like this. Okay, if you add 10 odd numbers, you can say that it is a 10 square. 11 odd numbers, it is 11 square. But always you should start with the number 1. Okay, there are a lot of more beautiful patterns like this that we're going to cover in next class. A very logic oriented questions are there, which we'll understand, and then we'll try to solve it in the next class. Okay, so thank you so much, students. Stay tuned to get the next lecture. Thank you.
Hello everyone, so now we'll be discussing about spherical mirrors. We already learned about plane mirrors, yes, now spherical mirrors. Okay, so my name is Shashan Reddy, I'm a graduate from IIT Dhanbad. Let's go into the class. So, where do we see spherical mirrors? Well, going to what they are, we'll go into that later on. But let's try to understand what or where do we see them in our everyday life. Look at this. What is this? This is a rear view mirror. And in this rear view mirror, you can clearly see that the image, you can see the images behind. So I'm driving in this way. The rear view mirror is here. So whatever object is behind me or behind the car, I can see that in what? In the rear view mirror, like this. Okay. Then, this. Nowadays it has become pretty common. Wherever there are turns, sharp turns, in shopping malls, shopping mall also, right? We are using these type of mirrors. They give a pretty clear idea of what is coming from different sides. Now, if you were to touch the mirror, okay, touch and feel the shape of this, you'll find a slight bend in it. It's like a slightly curved. Whereas in this case, you can easily see that this mirror is not straight per se, not like a plane like this screen, like TV screen, your TV screen. Is it curved? Is it bent like this? Is there any bulge? No. Right? But if you look at this, you can clearly say, this is not plain, it has a bulge. For a better understanding, whenever if you have a chance, you can touch it. Touch and see that it will not be like a TV screen, like a flat screen. It will be curved. It will be like a ball. Right? If you take a ball, cut it, you'll have a curve, right? It will be like that. Even this mirror, the rear view mirror also. So those mirrors that are not flat, that are not plane, that are like what? Like part of a ball, part of a sphere, they are called as spherical mirrors. Okay, let's understand them much more clearly. Okay, so you can actually do this at your own home. Take a steel spoon, a properly shiny steel spoon. Okay, now for a steel spoon, it has two sides. Right, if this is the spoon, I'll show it to you. It has two sides. One is this and the other is this. Right, now we give them two different names. One we call it as concave and the other we call it as convex. Sir, why are we giving it two different names? What for that? Why are we giving it different names? You can easily understand them by looking at yourself in the spoon. I told you, take a steel spoon. It should be nicely washed. It should be shiny. Take it. Now first, look at yourself in the spoon. Right? Just move the spoon towards you and away. Okay, notice what is happening. That's it. Notice the image. Then invert or reverse the spoon and again look at yourself. And see whether there will be any difference or not. And you will be shocked that there will be a difference. There will be a difference in the images that you see. That means both of them behave differently. That is the reason why we give them different names. For example, look at this. In one side we are getting what? An erect image, proper erect image, but here we are getting what? An inverted image. This is inverted image, right? See, head is down. Here head is up and here head is down. So inverted image. Right, so you can actually try doing it yourself. Do that, okay? It will be interesting and then you'll understand that, Here when I look at one surface or on one side, I'll get one image. And if I look at the other side, I'll get a different image, different type of images, different behavior, different properties. That is the reason why we give them different names. One is called as concave, the other is called as convex. So here this is what? The inside part, yes or no? Inside that curve, inside the spoon. So inside part is called a cave, like inside a cave, concave. Right? Whereas this is the outside part. Outside one is called as what? Is called as convex. It's very important that you remember these names, concave and convex, and also identify which is concave, which is convex. One side you have concave, at the other side you have convex. The inside of the curve, inside of the spoon is concave, outside is convex. We have many more examples, let's go into that also. You can understand this using a bowl also. Right, take a bowl. Now which is concave, which is convex? As I told you, inside is concave, like inside a cave, concave. So here, this is what? Concave, because it is inside. Concave is inside. Whereas convex is what? Outside. Convex is outside. This here is inverted. Understood? So inside is what? Concave. Got it? Outside is convex. Simple. Now you look at the animation carefully. We have taken a ball, cut it, and when we cut it, we'll get two parts, two surfaces. The inside one concave, the outside one convex. Inside one is what? Concave, and the outside one is what? Convex. Okay. Now let me show you something, everyone. We understood what concave and convex are, but now let me show you something. Mirrors. Now there's something in my hand and I have a concave mirror. Okay. So see this carefully. Obviously you will not be able to notice because it's very small. That is the reason. So I have a mirror in my hand. You can notice that mirror. Yes. This is the mirror. Look at the other side. Nothing, it's just a paint. So we say that it is silvered. What do you say? Silvered. This is a silvered side. Can you see your image in this? No, you cannot. But the opposite side, reflecting side, you can see the image on this side. And this is a concave mirror. Okay, if you feel it, I can feel that it is bent. It is bent, like curved inside. It's like a bowl. Okay, obviously, sir, it doesn't appear that way. Yeah, that's what I'm saying. When you see it, you cannot notice, but when you feel it, you can notice that. Okay, I also have a convex mirror. If I show you, it won't make much of a difference. It's the same. Okay, yeah. So coming back, concave and convex mirrors can be understood. Look at this, can be understood as parts of an imaginary hollow sphere. Right, here what did we do? Here we took a sphere like a ball. Ball is a sphere. The shape of a ball is what? A sphere. So you can think you have taken a sphere, cut it into parts. One part will be concave and the other part will be convex. Okay. Now one side is silvered. That is important side. One side is silvered, and wherever it is silvered, you cannot see, you cannot look into your image there. The other side will be the reflecting side. So the other side is what? The reflecting side. So what we are doing is, here in simple terms, we are taking a ball, we are cutting it, we'll get a bowl shaped thing. Right, now if I silver it on the other side, whenever we show it in this way, these dashes, what do these lines mean? These lines mean silvered. So here it is silvered. So you tell me, the outside is silvered or the inside is silvered? Outside is silvered. So which is the reflecting side? This will be the reflecting side. So we are cutting the sphere. We are taking a sphere, cutting it, and we are making it into a mirror. And when we make it into a mirror, it has two sides. One side will be called as the silvered side and the other side will be called as the reflecting side. Now here, which side did we make reflecting? The inside one, the concave side. So it is called as what? It is called as concave mirror. Concave mirror. But we can also do it in this way. We have taken a sphere, cut it, I'll get the bowl-like shape. Then what will I do? If I make the inside part silvered, the concave side silvered, then which is the reflecting side, everyone? This is the reflecting side, the outside one. Reflecting, it is bulging out, right? Reflecting side. And if it is reflecting side, and what is that? It is convex. So if the convex side is reflecting, it is called as what? It would be the convex mirror. So this mirror is what? Convex mirror. And why are these mirrors called as spherical mirrors? Because we are taking a sphere, cutting it, and then we get these mirrors. That means we are getting them from a sphere. Or you can say these are part of a sphere. That is the reason why we call it as spherical mirrors. They are in the shape of a sphere, in the shape of a ball, a round ball. That is the reason why we call it as spherical mirrors. Got it? Please take this down. Concave and convex. You should be able to draw the diagram. If you understood this, then you understood half of this, half of spherical mirrors. The most crucial part will be identifying which is concave mirror, which is convex mirror. Okay? Good. So, see that here? If we cut it here, the outside one is silvered, so light is falling on the reflecting side, which is inside is concave, so it will be a concave mirror. But if I cut another part, if I silvered the inside surface, that is the outside surface is reflecting and light falls on it. So outside is convex, so this becomes what? Convex mirror. Here it is concave mirror. It all depends on which side, which surface is what is the reflecting side. Understood? Good. Okay. So a very simple question for us. The inside of a shiny bowl is a dash surface. Inside, is it a concave surface or is it a convex surface? A or B? Very simple, straightforward. You answer this, you understood whatever we have learnt. And the answer is inside a cave, concave. Okay, just to remember. Right, you can think when it is inside, you have to think inside a cave, concave, right, rhyming. So concave. Good. So here concave mirror, that's what we are talking about, right? So this is like part of a sphere. I told you, right, part of a sphere. It's not a straight line. I showed you the mirror, yes or no? I showed you the mirror. So this is convex, that's the one I have. This is concave. This is the complete mirror. So the mirror will be like this. The mirror will be like this. So we are seeing it from the side. So when you see it from the side, what you can see? You can see a arc. That's what is shown here. The arc is shown. That's it. The arc. That's it. Okay. So you can see the silver coating protected by paint. Paint also will be there. And then the other side, the reflecting side, light will fall on it. Light will fall on the reflecting side. So obviously reflection is taking place on what? On the concave side. That is the reason why it is called as concave mirror. Which mirror? Concave mirror. Got it? Good. Convex mirror, the other case. You'll have the silver coating. It will be silvered. But the convex side will be the reflecting side. Light falls on it, and that is the reason why it is called as convex mirror. Clear? Good. So now image formation by a concave mirror. Okay, let me show you a video, but the complete video, the link is here. You can go through that later on. Okay, I'll not show the complete video, I'll only show a part of it.
This is a
So the volume is not required, I'll explain it. Okay, so it's, and this professor is a very good professor. I like his videos. You can start watching it yourself also. So see, what happens here is, I'll explain the situation. So this person here is standing in front of a mirror. Which mirror? Concave mirror. That's a concave mirror, you can see. So you can see his image also, the image of his face. Right, if this is the mirror, right, the professor starts walking back. Right, and when he starts walking back, what we have to notice is how the image changes. What we have to notice is how the image changes. So, shall we go into that? So watch it. So the professor is near the mirror. Watch it, the image is big, erect but big. And the image become huge now. It's huge, 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 huge. Very huge. Right? And then the professor is still going back. And you can see the head got reversed. Upside down. Upside down is inverted. The professor is still going back. Professor is still going back, and what happens is the image will be inverted, but the size of the image will keep decreasing. They'll show it to you again. They'll show it. Just keep looking at it. See, that's inverted, and as the professor starts going back, the image is becoming smaller. The image is becoming smaller. Okay. So I'll again play it to you. Watch it again. Watch it again. See. Okay. Watch this video again. Okay. Watch it again. See. Professor starts going back. So the image is first erect. Close to the mirror, image is erect. It becomes very huge. Huge. Right? See. Huge. And then as he keeps walking back, the image is becoming inverted. Image is becoming inverted, and you can see it in the mirror, by the way. It is inverted. And then as he keeps walking back, the image will be shown again. What happens? The image will be inverted, but the size of image keeps decreasing. See that? You can see the image now. The size of image keeps decreasing. And in plain mirror, it doesn't work this way. That is the reason why spherical mirrors are special. They are special. Okay. So what did we get until now? This is the mirror. I'll just take an example. If this is the concave mirror, we are talking about a concave mirror. So this is how it is drawn. So here, when the object is here, close to the mirror, the image is what? We are getting an erect image. But as the person goes away from the mirror, somewhere we start getting what? Inverted image. This is the object, okay? This is the object, don't worry. I'm just showing you what we understood. And as the person starts going back, then what happens? This height or size decreases. See, first, to some position, what happens? Size increases, yes or no? First, image is erect. The person is close to the mirror. And as the professor started going back, what we understood was image was erect, but it became huge. Size increased first. Then after some distance, it became an inverted image. And after that, the size started decreasing. This is what happens in the case of a concave mirror. Got it? Okay. Do you want to watch it again? I'll play it again to you, but this time notice this carefully. As the professor starts from near the mirror, as he starts going back, First you get an erect image and the size increases, it becomes huge. And after that you get an inverted image, and as it goes back, the size decreases. Okay? So watch it again.
This is a demonstration. Erasers here and here.
Watch it. It is erect now. The professor starts going back. See, it's becoming huge. So first the size increases. Then it becomes inverted, and after that, once it becomes inverted, what happens? The size keeps on decreasing. Just know this. Just notice those points. First size increases, becomes huge. You can say becomes huge, and then it becomes inverted, and then size starts decreasing. Got it? For a concave mirror. Good, wonderful. So for a concave mirror, I can also explain that in a different way. That is, if I go back here itself. If we come in the reverse way, while I am going away, size is decreasing. For example, here let's say size of image, I'll take an example, 10 centimeter, let's say here it is 5 centimeter, example sake. So when we are going away, the size is decreasing, 10 centimeter to 5 centimeter. But what if we are coming towards the mirror? From 5 centimeter it is becoming 10 centimeters. So size increases when you go towards the mirror. Yes or no? Away from the mirror, 10 centimeter to 5 centimeter, size decreases. Towards the mirror, 5 centimeter to 10 centimeter, size increases. Got it? Good. And then it becomes huge. And after that, while going away it is increasing, so while coming it decreases. Got it? Wonderful. Chalo. So we'll discuss that. And again, as we discussed, there are two types of images. We discussed about them already, everyone. Real images, virtual images. What are the basic differences between them? Real images are always inverted, whereas virtual images are erect. So if you are getting an inverted image, it means it is real. Erect image will mean virtual. Right? And then real images can be obtained on a screen. Here. Can be obtained on a screen. But what about virtual images? No, they cannot be obtained on a screen. Cannot be obtained on a screen. Got it? Basic differences. Obviously, real images, rays actually meet, virtual images, rays do not actually meet. Simple points. Okay. So if I come back to our case, for a concave mirror, I am getting both erect images as well as inverted image. What does that mean? Erect image will mean we are getting a virtual image. Inverted image will mean we are getting a real image. So, depending on distance from the mirror, you can get a virtual image and you can also get what? A real image. Both of them are possible. Good. So let's come back. Let's continue. So concave mirrors can give real and virtual images, both of them. A simple example is given here. So here it is erect. Erect will mean what? Virtual. This is virtual. And here it is obtained on a screen, first of all. So it is real. And if you look at the image, see the point, the tip of the flame is down. That is inverted will mean what? Real. So using a concave mirror, we can get what? Get both real as well as virtual images. Erect as well as inverted images. Okay, and for a concave mirror, real image can be obtained on a screen, that's fine. And virtual image is formed behind the mirror and cannot be obtained on a screen. Right, it is in the mirror, it's like in the mirror. So this is the candle, this is the mirror, and where is the image? Inside the mirror. It appears like it is inside the mirror, then we say behind the mirror. Okay. I think we have already watched the video for concave mirror. Yes? Good. When the object is brought closer to the mirror. So what is the basic difference? See here, look at the size of image. The size of image, the candle distance and the mirror. In this case, just a minute. Here, this is the candle, this is the mirror. Which mirror are we using? Concave mirror. And this here is the image. Image is inverted, so real, right? Now compare the same with this. Now look at the distance between the mirror and the candle. Distance decreased, or what you can say? Candle is brought closer to mirror. Candle is brought closer to the mirror, and look at the image. It is still obtained on a screen, real image, or it is inverted, so a real image, but the size of image has increased. So when the candle is moving closer to the mirror, the size of image increased. Did we discuss that? Did we discuss that? Look at this. Did we discuss it? Yes, we discussed it. So as the object is moved closer to the mirror, the size increases for a real image. For a real image. That's what we discussed, right? And when the object is very close to the mirror, very close, almost the same size. Okay. And what are we getting here? That is the important thing. We are getting a virtual, or sorry, forget about virtual. Are we getting an erect image or inverted image? When the object is close to the mirror, we are getting an erect image. And erect images are what? Erect images are virtual. Erect and hence virtual images. Okay. Okay, let's summarize all the points then. First of all, concave mirror can give us both real and erect, real and virtual images, or erect and inverted images. And when the object is very far away, the size of image is very small. Image will be very small. Real image, okay, it will be a real image. But when the object is moved closer, the image keeps becoming larger, size keeps increasing, discussed. At one point, image becomes the same size as the object. It should happen at some point. But is real and inverted. And image becomes enlarged and virtual. Yes or no? Virtual also, we got it. When the object is very close to mirror. When the object is very close to mirror. Okay. So images can be smaller or larger in size than the object. Yes, possible. We have seen it. And image may also be real or virtual. So all of them are what? Properties of a concave mirror. Now you should not mix up concave and convex. Both of them behave differently. Okay? Good. Then uses of a concave mirror. Where do we use it? For a makeup or shaving mirror, because as we have seen, when the professor was close to the mirror, we got a huge image, right? Erect image, but it was also huge, enlarged. Right, so if you want to look at my beard very closely, I have to magnify it. I'll use a concave mirror. Right, so makeup or shaving mirror, concave. We can use a concave mirror, yes. Then a dentist mirror, right? So dentist can look at the teeth, and if he uses it very closely, he'll get what? He'll get a bigger size of the teeth. So again, he can look at it carefully. Then again, it is also used as headlights in vehicles. Headlights in vehicles, as well as reflectors in torches. It's also used as reflector in car lights, headlights. Okay? Okay, good. Some uses of what? Concave mirrors. Simple? Okay. Then image formation by convex mirrors. Now convex mirrors, you can watch the video. You'll watch the video now.
This is a convex mirror.
The complete video, you can see that here. Don't worry. Okay, I'll just play it. We'll do the same thing here also. So see what the professor is doing. He's standing in front of the convex mirror. And you have to look at what? You have to carefully observe the image and tell me what's happening. See, observe it now. The professor will start going back and look at the image. How is the image? Upright? Erect? Is it smaller than the object? Yes, it is. So I can say it is smaller. Erect will mean virtual. Erect will mean virtual. So the professor can keep going back, but if you look in the mirror, it is always erect and smaller. That means, look at the point here, convex mirror always gives smaller virtual and erect images. Very important. Concave mirror will give what? Will give both real and virtual, but convex mirror will only give virtual, and that too smaller, right? Smaller images which are erect and virtual. Convex mirror. Simple point. You can look at that here also. Candle is the object, this is the mirror, and image is what? Image is smaller than the object. Good? Okay, wonderful. Uses of a convex mirror, very important. Side view mirror, rear view mirror, traffic mirror, security mirror, anywhere. Okay? Wonderful, good. So I hope you understood them. And a very simple fact for you. Have you ever seen a fun house mirror? Where like your head will be huge, your legs will be small, or your head will be small, your legs will be huge. Anything, it can be made in any way. So what happens is, just look at this. This is a fun house mirror, or you can find them in circus a lot. Look at them. Right, very funny images, right? Okay, so how are they made? It's nothing, it's just a combination of what? Convex, plane and concave mirror. Sorry, it's a combination of concave, convex and plane mirrors. That's it. Everything else is simple. Okay, so fun house mirrors are combinations of convex and concave mirrors, sometimes even a plane mirror. So at the same time, see, convex will always give us a smaller image. Concave can give us smaller as well as enlarged image. Plane will give us image of same size. So we use the combination of those three to make a very funny funhouse mirror. Okay. So we have a few questions, but I'll leave those to you because we don't have much time. I'll leave it to you. So please do practice them. Okay. Okay, so that's it everyone. We have learned about spherical mirrors, both concave and convex. So your task will be to identify concave and convex and understand their image properties. Okay, so thank you. Thanks a lot.